legs can be super easy. Meaning, if you had two different vectors written in components, which basically means not just looking at the vector u as a point u1, but a beginning origin to the end vector u. And if we looked at vector v as 1, 3, it'd be great to look at them this way, but if we had to do this whole shifty and connecty and then use a law of cosine z to do this, it could be kind of messy, it could be kind of gross. Not that it'd be impossible, but it'd be kind of rough. So if we can look at it in components and just put them together, man, we can add them, we can subtract them, we can multiply them by scalars and put them together. We can do all this crazy vector diagram work with simple numbers. But we have to have them in their components first. Now, I was going to do a quick example right there, but we're going to come back to where we are in this page, and then I'll do an example. So I want you guys to go ahead and write down this example first. If I start doing an example right away, I might lose you, and right now you're at least somewhat tuned in, paying attention. So, vector, help. Where do I need to put little arrows above letters? Which ones? The A, actually not. Okay, good. The I and the J. Because vector I is the little horse. Here we go. Vector I, he's a vector. Vector J, he's a vector. Who else is a vector besides I and J? That's close enough. Okay. We have I, we have J, and we have V. Are there any other places that we need them? No. Because little v1, v2 are just snazzy ways of saying my A and B, my legs. So if you want, if it helps, you could think about A, even though it's in the X spot, he is that X displacement. You can think about B as being that Y displacement. Wait a minute, isn't there another way of writing the A and B thing without I's and J's? What's the other way of writing it?
The parentheses things.
Close. You're right. They're in the place of parentheses, but they're triangles, also known as side carets. In English, if you're doing like proofreading, don't you sometimes do a caret to say like, hey, there's been a word omitted? Have you ever done that with proofreading, like not brainstorming, rough drafts? There's a caret. These are side carets. Or in your calculator, the caret means exponent, right? The caret means exponent. See those little side carets. With A and with B. Yeah.
I have a question. Why did we go from like 6.1 and 6.2 and then this is so much different from the others?
What was 6.1 and 6.2?
It's not log signs and log cosines.
The pause. That's just what the formulas were. What were we actually doing? I mentioned it yesterday.
Looking for sides and angles.
Of?
Triangles.
What kind of triangles?
That means that aren't right triangles.
It's all gonna match up.
They're called oblique triangles. They're called non-right triangles. Oblique triangles are non-right triangles. You guys have heard me say it, although some of you maybe for the first time are actually listening today. I've said it multiple times that vectors and triangles go together, and we'll see how, to be honest, if you guys just give me a second, today. So we have A and B, which come to a right angle. So if it was just this triangle in front of you, there would have been no need for 6.1 or 6.2 before we covered it, right? Because it's a right triangle, whatever. We could have done some Toa with it in like chapter 4. So why did they wait until after 6.1 and 6.2 to introduce vectors? Well, before we can get to the rest of it, I think we're going to have to finish this page because we still have to deal with the right triangle in front of us. So what if a problem gave us theta? What if a problem gave us theta, and we were trying to solve for A and B? Now, they didn't just give us theta. What if we were also given the magnitude of vector B? We were given the magnitude and we were given the direction. Oh, wait a minute. That's easy. That's despicable me, right? What if we were given the magnitude? What if we were given the direction? What if we were given magnitude and what if we were given the direction? How could we find A and B? You guys have hopefully set up this page of notes. So let me go ahead and give you a quick example. Okay? Just a moment ago, we were talking about vectors with like components of 2 and 1 and all this jazz. What if I was to say, yeah, let's just do this one. I'll dual screen it. What if they were to give us two vectors, and these were the ways they gave us the vectors. They gave us the magnitude of u being 50, the direction of u being 30 degrees, They gave us the magnitude of v being 30, and they gave us the direction of v being 110. Why would they give us this?
Because they're annoying.
Well, are they really annoying, though? Are they really annoying? If you were trying to head somewhere and it was an open field and you were trying to get to a destination, if you had a compass and if you were able to measure how far you were going, what would be the easier, more natural way to get there? For someone to tell, yeah, straight line. But here's the problem with a straight line. Couldn't it be at a diagonal? Right? So these ones are at diagonals. The shortest distance to get from here to here is just go straight there. Why go over and then up when you could just go straight? So practically speaking, the whole over and up, the whole component thing, isn't the natural way to move. The natural way to move is just to go straight there. Or like in vector v, it's not natural to go over and up. It's natural to go directly there. And especially if you're talking about things like gravity, well, it's easier to talk about gravity as going straight down. Okay, that one's straight down. He kind of has his components just because he's straight down. But in like a roller coaster, if you were trying to talk about a force that's acting on the person sitting in the car, that's like perpendicular to the track, it'd be much more natural just to show that vector, to talk about it with its angle and its magnitude, instead of talking about it with going over and going up in context of like north and south or horizontal, vertical. So Alex, I get it that maybe you can say they're being annoying once you see how hard this could be, but in all honesty, it's much more natural. Now, do you guys see that I have somebody who's drawn at about 30 degrees over here? And I have him going 50, which is technically, if you want to think about it, 5 units of 10. This one's going 3 units of 10, and I have it at 110-ish. Now make sure you have your little vector arrows over everybody, 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 everybody. Okay, vector arrows over everybody. Here's the dilemma. What if they were asking us for, it's at the very end of the whole paragraph. I know some of you have moved farther away. We might have to talk if it's too far away. But what is the word that I just circled? Who can see it? And you can shout it to the rest of the class if they can. Resultant. 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 What word do you see in resultant? Result.
The answer.
Yesterday, kind of the answer, but the answer to what? I don't see anything.
For the little legs.
Do you remember yesterday how we did the whole roller coaster thing? In the roller coaster thing, you had somebody in a car on a loopy thing, and then you have like gravity acting on it and the normal force acting on it. What was the name in the vector diagram of us putting those two together and trying to figure out its overall effect? Net what?
Net force.
Force. So in that context, we were talking about net force. Guess what the net force is or was? The resultant. You have all this stuff acting on something in one place, in one time, at one instant. And what's the overall result? So here's the snazzy thing of resultant. Resultant always means the sum of the vectors. Now if I just said that, you were like, yesterday that was easy. We take u, we add v, and we combine the x's, combine the y's, and we're done. What's the problem? We don't have the x's and we don't have the y's. Now, Jaden, you were asking why does this show up where it does? We were in a physics class. Well, if we were in a heritage physics class about 6, 7 years ago with Dr. Teague. He was a genius. He would have made us get out protractors, get out rulers, and we would have had to have literally, perfectly translated this vector, moved vector u, because right now they're working against each other. We need to think of them in tandem. Oh, I'm making it red. Red's the answer. We're not doing the answer. We're still working on the problem. So let's do this guy to be green. So he would have us go ahead and make vector u, shift him so we can think about the two working together on the same object. Yes, this is the practical, like, hey, there's the object. They're both working on it. But we need to move it and say, wait, we need to put them together. And to put them together, they need to flow into each other, head to tail. Where's my resultant supposed to be? From the very beginning to the very end. Now, wait a minute, hold on. I'm technically doing v plus u. Is that a problem?
No, because it's addition.
No, because addition is commutative. Even with vectors, there was a whole table that we kind of skipped. But it's allowed. This would be the resultant. We can call him, if you want, if you like it, we can call him R. Now, Jaden, what I just did is make an oblique triangle.
I know your thought.
And if I was to not do this page, if we were to ignore this entire page of notes, the only way for you guys with the given information on the screen to solve is to figure out a lot of geometry. Ready? You can say no. I understand, but let me show you the geometry. The geometry would be, for vector u, I know that he has 30 degrees and he has a length of 50. For vector v, we'll make him blue, I know that he has 110 degrees and a length of 30. Ooh, wait a minute. I moved this guy up, so isn't this 50 also? So I have 30, I have 50. If I had side angle side, I could use law of cosines to finish and figure out that resultant.
You have side angle.
I know. Side angle, that's that weird ambiguous case. We don't want to do that one. But wait a minute, what else do we know? Can't we be amazing and can't we go back to that good old-fashioned parallel line with a transversal cut thing? And couldn't we talk about how 110 minus 30, what's that little angle that's inside these parallel lines on the interior? I think that'd be 80, right? We subtract the two?
Yes.
Angle subtraction? That would be 80 degrees. And what are true for parallel lines of angles on the same side, the interior? They're not the same. Alternate interior are congruent. Yeah, they add up to 180. This is 100 degrees. If I wanted to draw pictures very precisely, and if I wanted to use a lot of geometry, I could avoid the page of notes that we're going to go back to. This would take a lot longer.
We can.
And then we would use side angle, yeah. Then we would use side angle side and say, oh, whatever, law of cosines. I got it, because all I need to do is solve for the length of the resultant, because they want of the resultant, the magnitude. Well, that's the length, law of cosines. We got it. But they also want the direction. Oh, no big deal. I can solve for angle. Okay, it's a little rough to see. I can solve for angle, well, I don't know, this dude. And if I solve for that dude, can't I figure out by subtracting from, who's this guy? 110?
110 minus 80.
I can subtract, well, it's not that easy. 110 minus 80 was this little,
No, 110 minus 30 is the purple one.
110 minus 80 would just give me 30, though. I need to get this guy, this little dude. And I don't see anybody that could find him except for the solving of the triangle. Right? I need to solve my triangle to get this little guy. And once I solve this little guy, then I can subtract that from 110 to get this guy, and I have my magnitude and my direction. There is an easier way, though. Do we want to pause and say, thank you, you said transversal, and I checked out? Okay.
I checked that.
Good. There's another way. There's another way.
checked
But
out
here's why it's coming after 6162. If I understand how vectors truly work and how I need to go head to tail to figure out the overall resultant in vector diagrams, technically it's all geometry, but it's harder geometry with oblique triangles. It's the law of sines and cosines that makes it possible. With the angles and with the directions. Now, hold on.
I have a question.
Yeah.
Why can't we just do side angle side?
No, we could. Oh. That's the point, is we could go do law of cosines right now.
Yeah.
But a lot of people just got really lost in the geometry of how I know that, well, 30 and 50 was easy, but how I know that 100 is this guy. And they don't want to go to law of cosines, even though the homework wasn't too bad, but law of cosines would find me magnitude. They might be kind of lost, but I don't think it'd be too hard to find this angle with law of cosines as well once I have side, side, side. I could find that angle pretty fast. But then trying to figure out, oh, hey, it's 110 minus that angle to get the direction would confuse them a bit.
I also have one more question.
Mm-hmm.
Why can't we find the yellow one?
Yeah.
If we just do 110 minus 80 to get the
30.
Yeah, so there's two 30s. I mean, it's just 60 degrees.
Wait, but where's the other 30?
You subtract 110 minus 80.
It's 30. 110 is blue minus 80 just gets you back to the beginning of 30.
Shut up, Emily.
No, do you see it?
No,
So,
I'm paying for different reasons.
no, I'm trying to, right here. 110, ready? Minus 80 is 30. It doesn't really give me any lunch pieces that I need. see it? We need the red, and the red is that line we don't know anything about. We need something with the red to figure out his angle. So we have to solve that.
Miss D, can I snatch your tape?
Yes.
Thank you.
Okay. So you guys, take a chill pill. I just need you to go back to section 6.2 law of cosines. I'm going to do all the hard work. You guys are just going to direct me. Okay? I'm going to grab up my calculator. I'm going to do all the hard work. You guys are going to direct me. I'm building up to why it's so important to figure out that page of notes that we've skipped and we're coming back to. Except all my calculators are done.
Should we use law of cosines for like a right angle, right triangle?
Technically, it'd just be way harder than
Yeah.
Socotello.
Yeah. Okay.
But technically. Okay, ready? You guys are looking at law of cosines? Okay. If I'm given, don't worry, I'm doing all the hard work. You guys are just watching because I'm going to teach you the shorter way. Given. So we've done all this analysis. We're going back to that page of notes in a second. But we're given side angle side. Okay, I need to find the third side. So question, what type of formula am I using? Side squared or cosine angle? If I need to find the third side.
Cosine angle.
No, side square.
Yeah, side squared. So I'm going to do this little dude squared, because that's technically that side that I'm missing. I could call him a variable if I really wanted to. I could call him an angle if a little lowercase letter if I really wanted to. I'm just going to leave him just like that. Now, his angle across from his is the 100 I had to use geometry for, right? That's this guy. Okay, so help me out. How do I use my 30 and my 50? Looking at the formula.
A squared.
So it'd be the one I know, right? Plus b squared minus. Okay, is that going to be a hard thing to solve, guys? Just thinking and remembering that homework, is that bad? No. Was the picture bad? For some of you, yes. For others of you, no. Okay, so we know what's hard. What's hard is setting it up, not so much the plugging in part. But we could plug in, and 50 squared, we got it, and then minus 2 times 30 times 50 times cosine of 100 in degree mode. I think I'm in radian. Oh, no, I'm in degrees. And we end up with, you ready? I square rooted both sides. We end up with this guy, his magnitude, half of my answer is 62.617. Got it. Okay? How do I find his direction? What law of cosine formula do I need to use if I'm finding an angle? The alternate form. So I'm going to say cosine of, okay, let's call this guy A. I'm making him the black. Cosine A. Okay, what side is across from him? We need that, right? 50. Okay, so help me out. What goes first?
50 squared.
50 squared minus,
30 squared.
oh, plus?
Yes, plus.
No, yeah, I'm pretty sure.
It's plus.
Is it A and little a?
Yeah.
Okay.
That's that, and then it's gonna be little b. Little b.
Sorry.
Yeah, it's little b. No, it's actually wait. No,
Isn't
it's
there
little,
a minus?
Yeah.
wait, no, it's little b. It's b squared. Yeah.
Oh, b squared. Okay. The 50 is supposed to go over here, I think. Doesn't the a go with the a and he's over here?
Yeah.
Oh, got it. I was really worried for a second. Here's my 30 squared, and here's my 62.617-ish squared. So it's the other two sides, these two that are straddling it, and then it's the 50 over here. And then I have 2 times, what is it, BC or A? BC. So I have to bring down that 30 and bring down that 62.617-ish. Now I'm going to use the full decimal. I'm not going to have error. We would do cosine inverse of both sides. Does the plugging in of this one seem crazy, just thinking about that homework that we did?
Yes.
I mean, in that homework, you guys didn't mind the law of cosines homework. You're just all freaking out.
I did. Mine was my calculator.
Oh, it was bad? No, the easier one's going to go right there. That's why you guys aren't writing this down. There you go. We have minus 50 squared, all over. We're still technically kind of answering Jaden's question.
Okay, Jay.
Yeah, thank you.
Eat your protein shake.
I'm done, actually.
You finished the homework.
He's a beast, what can we say? Times
You ate the food.
Dude, that was not.
62.617445592. Maybe I should have made you guys do it, because now you're just all tuning out. We end up with the final angle of A is equal to 51.847 degrees. Is this the direction of him? No. What is the direction
How
of?
do you know that it's not?
In my picture, didn't we go up 30 to get to that guy and up 110 to get to that guy? I need to know what the going up is for my R to know his direction. So I have all the pieces I need though. I know this angle. I need this angle. Who's the sum of those two? Who was this guy to begin with? 110. So what's 110 minus A? 110 minus that blah. 58.153. Okay. Why did I do all of that? I did all of that to first of all say, hey, how does law of cosines apply? It was the only way to solve the picture. It was the only way to solve the picture. Now hold on. Isn't there a page of notes that we haven't done anything with?
Sure.
Wasn't there something that we saw that was really snazzy yesterday about how to add vector u with vector v the easy way? What was really easy about adding vector u and vector v yesterday? They were in
Or brackets.
side carets, but yeah, they were in components. Just go that way. They were in components. It was so easy to add if they were in components. It was so easy to add if they were in components. Now, is it going to give me my magnitude and my direction? I don't know. Here's the problem. I just made for you the answer key. And you guys helped me a little bit with the law of cosines. I made for you the answer key. Our goal is there an easier way? Ready? If we can get those answers an easier way, well, let's just do it that way.
Be relaxed.
Okay? So hold on. There's the answer key. We know what the answers are supposed to be. Let's go back to this page that we skipped just a second ago. All right? Here you go. Pencils to paper, pencils to notes. We're trying to do this an easier way. What if, does this give you context now? What if we're given magnitude and direction? What if we're given magnitude and direction? And we want, ready? Check it. Do you see what this is doing now? This is saying I'm given this, and I want the components. Why? Because this is so much easier than the geometry stuff we think. At least you hope. Because some of you are like, wait, was that the easy way or the hard way? Okay, hold on. Were we given magnitude and direction over here? Yes. Did you guys just tell me it was easier yesterday to add because we just got to go down in components? Yes. So if we can change these guys to be these guys, ooh, life could be better. Now hold on, wait a minute. We have to go back to the right triangle, and we have to go back and remember, what's the relationship between A and these guys and B and these guys? What's the relationship between adjacent and a hypotenuse and an angle, guys? What relates A, adjacent, with hypotenuse and angle?
Cosine.
Cosine, thank you. Whew, you got there. Cosine of angle equals adjacent over hypotenuse. So can't we say, we can always find A, given those pieces, magnitudes and direction, by multiplying the magnitude times the cosine of the angle. And similarly, we can also do something with B, because it's an opposite over a hypotenuse, which means I can say B is equal to magnitude times sine of angle. And if I were you and you're a highlighting person, if I'm just saying, which I am, that this is the key to making things easier, I would highlight that puppy and be like, oof, if I have magnitude and directions, then I'm going to want to go to components. I need these formulas. Basically, it's just hypotenuse times cosine of angle is adjacent, and hypotenuse sine of angle is opposite. It's just a quick transformation. It's a quick rearrangement of SOHCAHTOA. And then, well, wait a minute, hold on. These questions are going to ask for magnitude and direction. Well, hold on. Let's go to our example. Let's use these first. So, I want to get, now, you guys, it's your turn. Calculate this out. I'm not making you do all the law of cosines because maybe we can avoid all of that. We have the answer key waiting for us to see if we can get there. How do we get the components for u? My A goes first, my B goes second, right? How do I get A? Which is magnitude, right? Magnitude, whose magnitude for u? 50. Cosine of whose direction for you?
30.
I can plug that in, no big deal, right? Wait. So who's B? 50
Oh, you're kidding me.
sine 30.
That is not okay.
Oh, so then you guys follow the pattern and get the same components for V. Because V, what's the only thing that changes?
The numbers.
The numbers. Because I'm going to do 30 cosine of 110, and I'm going to do 30 sine of 110. Yeah. I'm taking each vector and saying, who is your magnitude? Oh, you go there. Who is your angle? Oh, you go there. And I'm just plugging in for my A and for my B. But he has an A and he has a B too. So I'm using that snazzy like book notation because the book likes to use like these snazzy letters to be the A and B. But here's the cool thing. Do you guys realize that we could write all these decimals down?
Yes.
Or we could just take these and plug in.
Wait, why?
Well, because we're just adding down
What
anyway.
about the decimals? Why can't we just do the decimals?
You can write the decimals and then plug the decimals in and then add the decimals, but wouldn't it, don't worry, that's fine. Wouldn't it be nicer just to do, what was my U again? 50?
50 cosine 30.
Cool.
3 ones.
So if I'm trying to add all this, couldn't I just do 50, unless my keyboard doesn't work, cosine of 30, wow, the 0 really doesn't work, plus, wait, who would he go together with? 50 cosine 30 would go together with
The bottom one.
the bottom one, which is 30 cosine
110.
110. Look, I don't even have to, see, I don't have to write all the decimals to just add them together and be like, I have the components. Laurel. Yeah.
Class is such a big brain right.
Bummer. Where am I at? Maybe 22.258?
So do you recommend 3 decimals?
I do. Because if the book does 2, if we do 3, we'll probably be pretty safe. Does that make sense? 3 or 4. So I just need to plug into, oh hey, 50 cosine 30 plus 30 cosine 110. I have the component
My
of
class is
the
very different.
answer. Are you in degree mode? Oh, am I in radian mode? I might be in radian mode. Sorry, I didn't check this calculator.
I got 33.04.
Oh, I'm in radian. Thanks guys for double checking. Nice thing is I was using this one in degrees for the other one, or else I'd be so sad if I did all that work and it didn't work out.
That'd be horrible.
33.046. 33 point, what was it? 046?
Yeah.
Is that rounded? I didn't even look.
Yeah.
Okay. Wait, did you guys already find the other component? Because all you have to do is do the same thing, just change the cosines to sines, right? Change the cosines to sines. And what do you get for the next component? Same thing. You can actually, right? I mean, we can be super efficient with our calculator. We can go steal it.
53.19.
I get it. Can anybody match up with Alec and make sure he's good? 50 what?
53.1907.
Yeah, are we good?
Whatever you rounding it up.
Is it matching up?
Yeah, I was just not rounding.
So now I can be like, okay, wait, pause. Do you guys realize that I could theoretically have ignored this whole thing and just plugged into formulas and been like, haha. So wait, answer key.
Geometry.
Are we right?
Yes.
Pause.
That's the magnitude.
It doesn't take us straight to the answer, but it gives us all we need to plug into the formula. Wait a minute. There's more. Hold on. Haven't you guys literally just typed in 2 lines to your calculator? Technically? Pause. This whole picture was what was necessary. Look at all that. Do you see how much I have to copy and paste over here? Okay. This whole picture is what was necessary for all of this work. We had to do all the geometry, all the parallel lines, all the angle subtractions, etc.
I hate that so much.
Okay. Now wait. What picture is necessary over here?
Nothing. Oh, we just
Nothing yet.
Just a triangle.
Nothing yet. But check it. Nothing yet. I haven't graphed anything, right? But what am I gonna graph? 33-ish. So 1, 2, 3, and a little bit more. 33-ish, and then 1, 2, 3, 4, 5, and a little bit more. Okay, 33-ish and 50-ish. Okay, isn't it going to be like here-ish? Who is this?
That's the.
It's the red one that was
Along
over
the
there
way.
that I had to shift and then connect and then do all kinds of geometry. I've gotten straight to him. But what do I need to finish my answer?
The rest of the stuff.
The rest of the stuff. So I have my A, I have my B. How do I solve for the rest of the triangle if I have A and B? Pythagorean theorem will get me my magnitude, right? Oh, Pythagorean theorem, that's easy. So magnitude is just going to equal the square root of A squared plus B squared. Do you guys have these things in your calculator? You can just do that. The square root of goes stealing squared plus goes stealing squared. What do you get? Square root of the 33-ish guy squared plus the 53-ish guy squared. Caitlin's trying. She's almost there.
No, I don't.
So is Alec. So is G.
I messed up. Bro.
So
It
is
is trying.
No, bro.
It is under her jacket.
I broke it.
Kathy had it. 52 points. Ah! 1617.
Oh yeah, I got that too.
Hey, answer key. Okay, answer key. Do you get to avoid all this geometry?
Yes.
And all the log cosines, log sines, application to y's and
Wait, that's just the.
do you get to skip it?
No. Yes.
Well, look, I don't know. You tell me. Did it work?
Yeah.
It'll
So-
always work.
That just changed the notation from the bracket thingies to the number.
Yeah.
Okay.
It changed it from the over up to the natural out.
So all you did was put that in and then you got an answer and then there's
Can we do this? I hope so. All we got to know are the formulas and say add the x's, add the y's using the magnitudes and directions, and then throw it in Pythagorean theorem. Now, Alec, hold on, you were right. Like, that's just the.
Wait, so then do we have to do that?
That's just
Like
the
that?
It's just the magnitude. So what else do we need?
Direction.
The direction.
Hold on, wait.
It's a
Okay.
90.
I have an opposite, I have an adjacent.
Direction.
It's a right triangle. How do I solve an opposite and adjacent with
So
an angle?
Katoa
Yeah, who's opposite and adjacent?
sine. Wait,
Who's opposite?
tangent.
Tangent. So can't I say that theta is, wait a minute guys, what kind of angle is this? First quadrant, second quadrant, third quadrant?
First one.
Okay,
No, this is no reverse.
so let's use tan inverse and let's see if we end in the first quadrant. If we do, we're done. If we don't, we might have to like add 360 or something random like that, but we'll look at it. We need a first quadrant angle. All we're doing is opposite over adjacent. Tan inverse takes us backwards. Opposite and adjacent, tan inverse gets us, well, hopefully. Has anybody gotten 58.153 yet?
I have the thing down
I
there.
put the wrong number in.
Caitlin just gave me a head nod, so I'm filling it in.
What did you plug in? I completely zoned out. Oh, I did the wrong.
Oh, we plug in the y component over the x component because opposite over adjacent with the tangent inverse will take me there.
How do you know that was B?
Because to find the direction of this guy, I not only want his magnitude but also his direction. I use the opposite and the adjacent because that's what the components are. It's a lot easier than a lot of cosine.
Why is it inverse though? Oh, I put the over.
Oh, I didn't set up the overflow. It's inverse because, ready?
Oh, I'm trying to find an angle.
Isn't there something else we haven't filled in yet?
The other angle.
What does this one say? How to solve for theta, given A and B. How to solve for theta? We can use tan inverse of B over A. I'm going to say use. And then, Emily, here's what you're asking. Since tangent of the angle is the opposite over adjacent, and so how do I get to angle if it's stuck in a tangent? Tan inverse both sides. So how do I get to theta?
Oh, because I used the.
If I have a tangent, is I need to take tan inverse of both sides.
Oh,
So tan inverse of this side would get me to theta, and tan inverse of this side will help me. Now I have to look at the picture to kind of know the first, second, third, fourth quadrants. Don't worry, the simple picture, not the hard picture. Yep. Use tan inverse. And then I'm going to say, get into the correct quadrant. also, give me 1 second, Dean. I'm also going to say, how do we solve for F to get theta? And we already wrote this one down, but just to make sure you guys have it, because this is all on the same page, then we can use the, remember, a squared plus b squared square rooted to find magnitude. So we can find direction.
And magnitude.
And magnitude. Jaden, what's your question?
Okay, so
This
for that
literally
example,
is
so
a
basically
so
you use
exclusively
What,
close to
Alex?
something.
It's a productive question.
Oh,
Go ahead.
I think it's real.
I think it is too. Go ahead.
Okay. So you basically use the u plus v thing, like to get the 50 codes. Or I don't know how you.
Yeah. The u plus v formula, right?
Yes.
Yeah.
Okay, so you did that.
Good.
Okay. And then I don't know. Okay. So what tells you to use that? Is that that's the resultant?
The result. Well, that's the hard part, right? Because in the paragraph, how would you know unless you knew the resultant is the overall result, which comes from adding them all together, which is so much easier if you just have the components.
Okay. So are there other words that would tell you?
Good call. They could actually say sum of the vectors, which is a little bit easier. So you're like atom. They could say resultant. They could say net. Net means overall. So net force, net this, net that. Net change. So they could say net change, they could say resultant, or they could say sum. That's about all they're going to say. But all of that means put it together. And to put it together, it's so much easier if you have components. If you don't, make them. Because then, whoop, we got straight to the answer. All we got to do is solve our little baby right triangle for hypotenuse and HPA. You see it? Priyanka.
So I understand that the harder way to do this is using law of sines and law of cosines. But if this is the better way, then why do we need to have that before this?
Because we're showing you kind of like where you can get to based on rewriting these vectors in another sense. But technically, if anyone mentions vectors, how do they usually mention them? Is magnitudes and directions. And so therefore, like we do have a lot of triangles that are involved. And if it was just two vectors, to be honest, we might just stick with the law of cosine, law of sine stuff and have you keep practicing that. But the dealio is, to be honest, guys, there usually aren't just two forces in action. There could be 3 or 4 or 5. And imagine having to go 1, then 2, then 3, then 4, then 5. If you connect that, is that a triangle anymore? So the problem is if you have more than 2, as soon as you introduce a third or a fourth or a fifth, all of a sudden you would have to keep track of triangle upon triangle upon triangle upon triangle. Because it's not just one triangle. Only 2 vectors added together will be a law of sine, law of cosine. As simple as that. But anything more advanced, we would just break them all down into little baby right triangles. So that kind of begs the question, in section 6.1 and 6.2, could we have broken all of those pieces down into little baby right triangles and put them together? Maybe.
Yes.
Maybe. But sometimes if you just have a triangle and it's not in context of something else, it might be easier to have a law of sines, law of cosines. But long story short, like the geometric way to solve this, you wouldn't be able to do without it. So that's an example. So guys, here's the dilemma. Did we get through all the content?
Oh,
Yes.
Yes.
What did we not get to practice?
Word problems.
problems.
Thank God.
Word problems. But we do have all of the information to get up to word problems. So what I'm doing right now, I know the bell might ring before I'm able to totally finish it. I'm going to go ahead and go over here and go into your Google Classroom, wherever it may be. It's kind of chilling. And I'm going to go ahead and make the homework that is due on Monday submitted by 8 a.m. I'm just going to make it everything but the word problems. Okay? So you guys are just practicing the basics. You're practicing the formulas. I'm also going to do a quick note check. I know we had a lot of different days and a lot of different content. I'll give you 3 points for having your notes up to date, ready to go in chapter 6.